I would like to express my appreciation, bordering on admiration, for the splendid organization of this meeting. I attended several meetings of the Polish Physical Society, and this is indeed the best. And I think that one should really thank Arkadiusz Voice for the efforts to make this a memorable experience. My talk, in a way, is orthogonal to what we heard from Professor Hensch. It will be, to some extent, technical, but I do hope that I will convey some philosophy that I think is not really shared by many people who work in this field. Of course, there are true experts who will find what I'm saying quite obvious, but on the other hand, reading the literature on the subject of optics, quantum optics, optical beams, I can assure you that there are many misgivings and many notions are misinterpreted. Who needs quantum mechanics of photons? Many people would say we have quantum electrodynamics. It's a theory of quantized electromagnetic field. But it turns out that it's rather difficult to see some subtle issues when you look from the point of view of quantized electromagnetic fields. And these issues have become more important quite recently because there are new resources in optical beams that are being used, which are connected with angular momentum, polarization, etc. Well, let me start from an old quotation from Willis Lamp and Company, who wrote that photons really, as particles, are a very illusory concept, and perhaps one should get rid of them. But this issue has been resolved many years ago by Eugene Wigner, who wrote a long, long paper in Annals of Mathematics. But this paper is, of course, unknown to the quantum optics and optics audience, so I will present, among other things, a brief summary of this paper. Well, there's no doubt that photon is an elementary particle. It exists in the table. Right here, you see the photon. It is an elementary particle. And as such, the photon is subject to the laws of elementary particle physics. And since this is an elementary particle, we can proceed with treating it as a particle before we turn to electromagnetic field, and I will make this connection later in my talk. Well, what Wigner has done? Well, he made a theory of all possible entities which can be called elementary particles. There was a long list of possible elementary particles from the point of view of relativistic invariance. We know that relativistic invariance is a very well-seen symmetry in the universe, and one can ask what are possible particles that would fit into this relativistic framework. So the mathematical content is called the theory of representations. Each entity, photon, neutrino, proton, whatever, is an entity which fits into this relativistic scenario. And Wigner said that there are two kinds of photons which are distinguished by their transformation properties under Poincaré transformations. What are Poincaré transformations? These are Lorentz transformations. That means ordinary rotations, and what is called boost, that is transformations to a moving frame. And in addition, that would be the Lorentz transformation. In addition, we have just ordinary translations. We can shift in space, we can shift in time, and that makes the Poincaré group of transformations. So we have these two kinds of photons which are completely different, and under all transformations, Lorentz transformations, translations, they transform differently. And this is the first thing that is often misunderstood. Since they transform differently, we cannot take the wave function that is describing the left-handed photon and the wave function which is describing the right-handed photon and put them together, add them. This is not allowed because these are different representations. So this is first thing that is often misunderstood, because one would say if we have left-handed photons and right-handed photons, by putting them together we get linear polarization. Well, that's not that simple. One has to be more careful, and I will explain that in a while. What can we do now is to introduce quantum mechanical description of these photonic states. We need two wave functions. One wave function which describes the state of the right-handed photon, another wave function that describes the left-handed photon, and we cannot add them together, but we can put them in one two-dimensional object which can be viewed as a wave function of an arbitrary photon. Notice that there is some analogy between photons and electrons. We also have two states of electrons when it comes to spin. There is an electron with spin up, and there is an electron with spin down, and we never add them together, but we put them in a column which has two components, and this is called the Pauli spinor that describes arbitrary polarization of the electron. And this is the same for photons. When we have these two wave functions, we can define the norm of this wave function, and these wave functions have standard interpretation, like in quantum mechanics. The modulus squared of the wave function is the probability density. This wave function is telling us what is the probability to find the right-handed photon and the left-handed photon with the wave vector equal to k. So this is the rudimentary description of quantum mechanics of photons in momentum space. Now what we need is the dynamics of these photons. And for that I again use what Wigner did, namely what are the main operators when we use this quantum mechanical language. Well, these are connected with the transformations of the Lorentz or Poincaré group. Translation in time is generated by a very important observable, which is the energy, the Hamiltonian of the photon. The time translation then can be connected with the Hamiltonian, and the space translation is connected with momentum. When we want to move, to translate the wave function, we apply the momentum and we move it. Then, of course, we have important, very important, observable, which is angular momentum. There are three components of angular momentum, and these three components are written here. Notice that there is the part here which looks like orbital angular momentum, and there is an addition here which is connected with helicity, spin, polarization, as I will explain later. And now it's just what Wigner did, that is, he introduced the generators of transformations, and these are connected with physical, dynamical variables that describe this dynamics of the photon. Now, you see these plus-minus signs here. They refer to right-handed photons and the left-handed photons. They have different transformation properties. And in addition to this, we also have the operator, which is taking us from one inertial frame to a different inertial frame, and they are called the boosts. Well, there is some interesting mathematical subtlety here. Light cone is not really flat, because light cone has the singular point here from which it originates, and the presence of the singular point makes the geometry of light cone non-trivial, and therefore translations in the light cone are not quite trivial. There is some curvature involved, but that is not really important at this stage. So what is polarization of the photon? Polarization is just the degree of freedom which results from having these two components. And the best way to see this degree of freedom is to say that suppose that these two wave functions have the same dependence on k. And there is upper one and lower one, and since they have the same dependence on k, the only difference could be that they have different intensity, so to speak, of the right-handed photons and the left-handed photons. This will come later in my talk, because helicity is a quantum number which is absolute in free space. However, in practice, we have photons all the time interacting with matter. And interaction with matter, when photons hits some material object, it will change its helicity. Therefore, we must allow for changes of helicity from one right-handed, left-handed. There are various polarizers that everybody knows that change the helicity. In free space, helicity is absolute, cannot be changed. However, when photons hit something material, they will in general change their helicity. So here is an interesting quantum mechanical concept that enters. This is called the entanglement. When we have systems that they have different degrees of freedom, then the quantum mechanics allows for something which is called entanglement, which is the essence of quantumness, one may say. Entanglement, and that has already been noticed by Schrödinger, is really in the heart of quantum mechanics. That's what causes all these effects that are very hard to understand, like, for example, the famous Einstein-Podolsky-Rosen paradox. This is due to entanglement of different degrees of freedom. So now we come to position representation. That was all about the photons described in momentum space. What is their spectral character, one may say. But now we want to know how these photons behave in space. So we must construct what could be called in the ordinary Schrödinger mechanics the Schrödinger representation, wave function in space and in time. So This is usually done with the help of Fourier transformation. However, there's a big problem here. If we just take f here and Fourier transform, we get an ugly object which has no neat physical properties whatsoever. It's not local in space, which means that if we perform a transformation, then after the transformation, the wave function at this point will not only depend on this wave function at the point that was at the origin, but it will depend on the wave function everywhere. So it's an ugly object, and to cure this disease, one must introduce something which I will call scaffold, which enables us to produce a good object here, a field that really is a function of space and time and does not depend on, after the transformation, on the wave function everywhere. So this is the object, and one can study this object. E plus minus here is a vector which is a very good, well-known concept from standard electromagnetism, is the polarization vector. That's the polarization vector for circular polarization. There is right-handed photon, which has the right-handed polarization, and this is the polarization vector for right-handed and left-handed, and we have two wave functions. At this point, we still have propagation in free space. There's no interaction with the material, and therefore we need two wave functions to describe two photons. Left-handed and right-handed photons, they have separate wave functions. Now we must ask the question, where is the electromagnetic field? After all, electromagnetic field is made of photons. There must be some simple connection between the electromagnetic field and the wave function of the photon in space-time. And this connection is really very, very simple. Namely, if we have many photons, then we produce macroscopic field. If these photons are all different, then the macroscopic field is some ugly state that contains photons with various properties. However, there are some electromagnetic fields which are produced by lasers, and these electromagnetic fields are really such that all the photons are the same. And therefore, we can use the photon wave function to describe the electromagnetic field, because this is built in a coherent way. Otherwise, it would be much more complicated. We would have to consider even mixed states, and etc. So what is the connection between the electromagnetic field and the photon wave function for such simple situation when all photons are the same and they produce this macroscopic laser field that Professor Hensch uses for his tricks? And it's very simple. The real part of the wave function is the electric field, and the imaginary part of the wave function is the magnetic field. Of course, we have two kinds of photons. They produce electromagnetic field which is right-handed. That is, it has right-handed circular polarization in the terminology of standard electrodynamics, or it has left-handed circular polarization in this terminology. And the structure of this function, this here, will lead to Maxwell equations for this electromagnetic field. It can be written in this nice way as one equation, but taking real part and imaginary part. Notice this imaginary unit. So when I take the real part of the left-hand side, it will be the imaginary part on the right-hand side because of this unit. And this is what happens in Maxwell equation. Electric field differentiated in time produces the curl of the magnetic field, and the reverse, the time derivative of the magnetic field produces the curl of the electric field. So we do have the Maxwell equations, and that is the connection with standard electrodynamics. But let's proceed now and discuss some very important issue here. Well, we notice after Wigner that momentum, angular momentum, energy are acting operators, as always in quantum mechanics. They're operators that represent physical quantities. They act on wave functions. And the same is true in the position representation. We have the operators, which are the same operators that I have written before, but now they are translated by this Fourier transformation to the space arena. And what happens? Of course, this is a well-known object, the derivative multiplied by minus IH. The Hamiltonian for the photons is quite simple. It's just the scalar product of this S here and the gradient, and there's angular momentum. What is S? You just open the textbook on quantum mechanics and find the spin matrices for spin 1. For spin 1/2, these would be Pauli matrices, but since photons have spin 1, we need the representation which is good for spin 1 particles. And indeed, this looks familiar. Angular momentum has two components. Angular momentum of photons has the orbital angular momentum, which is clearly written here, which is a cross product of position and momentum. And there is some additional part which is connected with this object. And this requires certain care when we want to interpret this. Indeed, this is a well-defined object. When it acts on wave functions, it produces different wave functions, as it should. However, the splitting between orbital angular momentum and the spin part does not make sense. What does it mean? If I take this operator here and act on my wave function with this operator, I get a function. That's indeed quite trivial. I have to differentiate, multiply. But is it a good function? Is it still a function that represents a photonic state? No, because this function which I get by this operation here will not be allowed, since its divergence is different from zero. Divergence of the electric field and the divergence of the magnetic field must be equal to zero according to Maxwell theory. Maxwell theory tells us that in free space there are no sources, so to speak. In particular, there are no magnetic charges, so the divergence of magnetic field must be zero. But it is not so if one takes just this up. And of course, the same is true for this part. However, the sum is well defined. It produces good wave functions. So here we see what is here non-trivial. One cannot say that the spin of the photon is a well-defined concept. It is not, even though it enters into the object which is good through angular momentum. Now, why is this related in a simple way to optical beams? Once we have this quantum mechanical description of photons, we can now translate this quantum mechanics of photons into the language of electrodynamics. If the photon state has well-defined angular momentum, say z component of angular momentum, then the electron beam, photon beam, has also well-defined angular momentum. And such beams are quite important now. There are various properties of these beams which are used. Professor Zeilinger uses this resource to transmit information, for example, which is stored in angular momentum properties of the beam. This is an additional degree of freedom. We know that we can use phase and the amplitude as the resources of the electromagnetic wave. But in addition, there is this new resource, which is angular momentum, which can also be used to store and transmit information contained in the electromagnetic wave. So now we come to the standard description as I did it for the momentum representation. This is, of course, the connection with polarization. This is the general wave function, which has the right-handed component and left-handed component. And when these spatial properties are the same, we have just two amplitudes which are not functions of R and B. And when A is equal to B, this particular state is the linearly polarized wave. What is important here is to appreciate that polarization is not a relativistic concept, because these two functions transform differently. Therefore, what is linear polarization in one frame is not linear polarization in a moving frame. It becomes then a different polarization, elliptical polarization, more general, even though in some frame it is just pure linear polarization. There's one thing which I have to mention in connection with this whole concept of quantum mechanics of photons. We know that at the very heart of quantum mechanics lies Heisenberg uncertainty relation. So since we have here a good quantum mechanical description, the question is, does Heisenberg uncertainty relation generalize to this situation? Yes, it does. One can prove mathematically that there is an inequality here, which is written here, which is different from Heisenberg, because instead of 3 halves, 1/2 for each degree of freedom, we have 5 halves. Why is that so? Because photon has helicity. Therefore, its spreading in space is somewhat different from what we get for non-relativistic particles. And the definition of delta R squared is just the standard one, except that instead of the Schrödinger wave function, we have to put this photon wave function in position space. Well, we have well-defined photon wave function in momentum space. There is no doubt that this is a good definition of the momentum spread. And of course, we have to normalize this. Mistake. There is no n in the denominator. That's by copy and paste. This is just the definition of the integral here. Sorry for that. And then one can prove mathematically in a similar way, even though the calculation is more complicated, that the uncertainty relation reads in this way. So what is now the summary here, which I hope you will remember from my talk, that quantum mechanics of photons is a well-defined theory. It was really originated by Wigner, and there is no controversy about this, because this is a mathematical, 55 long pages long paper, and Wigner was a very good mathematician in addition to being a great physicist. And he just produced a theory of all possible representations of the group, and they are associated with particles. Most of these particles do not exist in nature, but some of them do, and they are described by these representations. Once we have a representation, we can then identify the dynamical properties of these objects: energy, momentum, angular momentum, whatever. So quantum mechanics is a well-defined concept. Now we also should remember that polarization is a tricky concept, because at the very bottom, the most fundamental properties of photons is helicity. Are they right-handed or left-handed? When one reads standard text on electrodynamics, one has the impression that right-handed and left-handed is not any better than horizontal and vertical. They seem to be treated on the same footing. Sometimes even one makes the impression, the authors of the textbook make the impression that linear polarization is the fundamental concept, and right-handed and left-handed are secondary, because linear is clearly seen as being defined by the oscillation of the electric vector, and these oscillations are in well-defined direction. Then we have linear polarization, and circular polarization is secondary. Not so. Polarization of photons originally is circular, right-handed or left-handed. The rest is just a secondary concept. So I also hope that I presented the connection between photon wave functions and electromagnetic field, which is this bridge that bridges quantum mechanics with electromagnetic field. This is the bridge between corpuscular and wave nature of light. Thank you.
Thank you very much for this illuminating lecture. Marek.
If the spin of photon is not well defined, then why do we think it's a boson?
The notion of bosons is in the symmetry of the wave function. The wave function of one photon does not tell you whether it's a boson or a fermion. However, when you have a collection of photons, then the fact that the wave function is symmetric under the permutation of the indices is connected with the bosonic nature. In a way, spin here is integer, because helicity is equal h bar, and helicity for massless objects replaces spin. Why is this difference? That's a very good question, because I can say something quite important which probably was not clear. Spin of an electron can be manipulated separately from the position. One can rotate the spin, and there are various devices that do that, magnetic fields whatsoever, they rotate the spin. For photons, one cannot rotate the helicity, because helicity is always connected with the direction of propagation. So in this sense, the spin of the photon is different, and fundamentally it is the helicity. There is a secondary concept of spin which enters into the definition of angular momentum. The total angular momentum has definitely two parts, but the spin conceptually is not the same as spin of an electron, because it cannot be separately manipulated. You cannot leave the direction of propagation and turn the spin, because it is always aligned with the direction of propagation.
We shall thank Professor Białynicki again.